Hi, everyone. So I'm Martin Feussner from the University of Bergen. Igor Semaev is my supervisor. I'm his PhD student. I'll be presenting EHT version 3 and version 4, which is a scheme that Igor himself came up with, and I just implemented it. I only joined him this year. So I'll just provide a quick overview. This has some similarity with the public key crypto system EHT, which he worked with his former PhD student, Bergen. Igor has made prior versions, EHT version 1, which is available on ePrint, and EHT version 2, which he presented at some conference in Stavanger, I think. EHT version 4 is very similar to EHT version 3, but the arithmetic is in a finite group ring GQ over ZQ instead of ZQ itself. Schemes are easy to understand and implement, and I can definitely attest to that, coming from a non-cryptography background. Parameters can be easily modified to increase security levels if needed, and hardness is based on solving some linear algebra problems, such as closest vector problem. Now I'll set up some definitions for EHT version 3. So A refers to our public key matrix, C, T, and B are our secret key matrices. And the public key matrix is just computed as a symbol matrix multiplication of C, T, and B inverse. When I use the congruent symbol, I mean imply mod Q everywhere. And C is constructed as by two submatrices, C1 and C2, where C generally is a sparse matrix, and the one norm of each row of C and C1 respectively is lambda and tau. You can see that C1 is a square matrix, and you can also deduce from this that M plus D is equal to K times N. Then we have T, it's a special rectangular matrix, our trapdoor. It contains diagonal tuples, right? It contains tuples on its diagonal, which you can see in the structure that tries to summarize it. So we have the tuples on the diagonal with random entries below them and zeros above them. And B is an arbitrary matrix that is invertible modulo Q. Now, the core theorem in our submission is stated as theorem 1. For every A element of Z, K, N, Q, there exists Y and Z such that the max entries in Z, such that the entries of Z are bounded by C in absolute value, and A is congruent to Ty plus Z. Because T is triangular, it allows us to solve systems of equations to recursively construct Y and Z that satisfy the above, and this is done efficiently. So some further definitions. H will refer to the hash of the message. As I've shown, A, Y, and Z are part of the core theorem. E is the error vector, X is the signature, and I've stated the dimensions in there. And for version 3, level 1 security, M and N and L are the variable. Those are the values for M, N, and L. And across the different levels of security, these are the variable parameters. And for Q, K, lambda, tau, C, and S, they are fixed across all levels of security. And I've also noted here max LE, meaning that at least L entries in E are bounded by S in absolute value. So these are the sort of the main, or basically the formulations of the scheme. So we have A times B is congruent to CT, CA is H, A is TY plus Z, E is CZ, and X is BY. And we can see that from the first equation, we can compute our public key. And from the second one, we can split A into A1 and A2, as I've shown before. That allows us to solve A1 for some fixed A2, which we'll see later. Y and Z are solved from the core theorem. And as you can see, E evaluates to H minus AX, which is used in the signature verification. So the key generation, we initialize some random number generator with some C that is part of our secret key. We generate C1. And we go back to 1 if C1 is not invertible. And then we generate B. We try and compute B inverse. If it's not invertible, we go back to 1. We generate C2. We generate T. And finally, we compute the public key A. Now, the signature generation, we initialize the random number with our seed. And from that, we have C, T, and B. We compute H using the message. We random generate sum A2. We compute A1 as I've shown. We compute Y and Z by theorem 1. And then finally, we can compute E as ZZ. And if at least L entries of E are bounded by S in absolute value is not satisfied, then we go back to 4. And if it is satisfied, then we can finally compute the signature, which is just B times Y. And finally, for signature verification, we simply just compute E is equal to H minus AX. And you can verify the signature if at least L entries of E are bounded by S in absolute value. Some general improvements we have made to version 3 is that we can check if C1 is invertible from its characteristic polynomial, which I'll denote as PC1, determined from its Hessenberg form, which can be stored as part of the secret key. It allows us to speed up the signature generation process by applying Cayley-Hamilton theorem when computing A1 at the cost of a larger secret key. And we can also compute an invertible B by construction, which I assume most of you already know. And that makes the key generation look much simpler, where you just need to set some seed for an invertible C1. Now, regarding cryptanalysis, I just present a few of them here, and then we'll continue from there. Okay, so private key recovery and algebraic attacks. So the focus of this attack would be when we have C multiplied by the last column of T, and that gives the equation of the last two columns of C. And T here denotes the diagonal element, one of the elements from the tuple, right? In our scheme, K is equal to 4. So the diagonal tuples are of size 2. The first entry of the tuple is 1, and the second entry of the tuple is just 2C plus 1, because that satisfies some equations that are set up, which you can find in our submission. So that sets up this equation. This leads to M linear equations with n plus 2m unknowns, resulting in q to the power of n plus m potential solutions. Alternatively, we can guess n0 entries of some v, which is equal to that expression, and solve n equations with n variables. And the success probability for this for version 3 level 1 is approximately 2 to the power of negative 246. So suppose it has to be secure. Number 2, existential forgery by guessing. Given that H is just the hash of our message, one may guess small values bounded by S in absolute values for some n entries of E, and then compute X by solving a system of n linear equations modulo Q. One then checks amongst the remaining entries, which is m minus n entries of E, if at least L minus n of the entries are bounded by S in absolute value. And then we can set up a probability, and we can derive that this probability, success probability is expressed by that equation. And that's just the success probability. And then considering the number of operations modulo Q, an optimized attack would roughly take 2 to the power of 140 operations for version 3 level 1. Adaptive forgery under known message attack. A message M with H may have multiple valid signatures because each message has multiple valid signatures. And suppose for each one of them we have the corresponding error vector. We can modify some new message with its signature to get that expression. And it'll only pass as a valid signature if if at least L entries of that expression is bounded by S. Assuming that entries of E are independently distributed, the probability of this is expressed by that. And for version 3 level 1, this is equal to 2 to the power of negative 101. And therefore, we would require a little over 2 to the power of 101 independently generated triplets for E0, E1, and E2 for the attack probability to be close to 1, which is greater than the cap for this analysis indicated by NIST, which is 2 to the power of 64. Now, coming to version 4, it is pretty much the same as version 3, except everything now happens in a group ring, GQ, right? So this allows us to create some large factor of compression for our public key, but at the cost at a slightly larger signature. G contains R elements, and that's the order of the group, and you can express it as the formal sum of its elements with the coefficients from ZQ. So for version 4, level 1, we use the group PSL, which is a projective special linear group, 2, 7. That is basically all 2 by 2 matrices over Z7 that have a determinant of 1. And the group size is 168. The order of the group is 168. And visually, we can represent the public key as C times T times B, right? So we can see from here that M, N, and K are 3, 2, and 2 respectively, right? And we have different norms now for the matrix C. And with version 4 level 5 security, we use A6, the alternating group, on 6 elements, which has an order of 360, sorry. Now, improvements in version 4, when checking if C1 is invertible, we compute the inversions of resulting diagonal elements. These inversions can be stored as part of the secret key and allows us to skip any inversions in the signature generation process, which is the most computationally expensive operation in the scheme. We can also create an invertible B by construction, as you can see. Now, coming to sizes and timings for both versions. As you can see in the signature, version 3 does much better than version 4 by almost a factor of 2.5. Right? And private key sizes, again, version 3 does better, but when it comes to public key sizes, you can see that version 3 public key sizes are in the very high kilobytes, whereas version 4 is pretty small. Our key generation times are expressed in milliseconds. I mean, all the generation times are expressed in milliseconds here. Version 3 only does super fast for us in the signature verification process because it's just a simple matrix multiplication. But in version 4, it's slightly slower. And those are the specifications of my personal laptop that I use to run this. Now, compared to other schemes, comparing the sizes, for level 1 security, Falcon has the best, and you can see the highlighted portions for where each one falls. Version 3 does best in terms of its signature size, but at the cost of the ridiculously large public key, right? So version 4 provides some sort of middle ground to all of this. And if version 3 wasn't in this picture, then version 4 would have the shortest signature, which is still relatively well. So far there have been 2 published attacks from the forum, one by Wessel and Ehrman. Sorry, I'm very bad with pronouncing names. They're from Team Hawk. So the attack is given A and H, a BKZ attack, base attack finds E and finds X and E1 such that E1 is equal to H minus AX. And the max, at least L entries of E1 are bounded by S in absolute value. They recently broke our challenge of 80-bit security, 80-bit security. So our countermeasure that we have noticed that E and E1 are distributed differently. We would take a real value distinguisher function, F, with some bounds B1 and B2. And so that will create new rules for the signature generation and verification. So we had that at least L entries of E are bounded by S in absolute value. Now we have this extra condition. And so far, when we have run at least, when we have checked with at least 1,000 signatures generated by the attack, none of them passed this verification. They passed the first verification, but not the second one. But we will further study this probability to better the choice of F. So for the attack, only the upper bound is sufficient, but we believe that a lower bound is also required for a different version of the attack. Second attack by Keegan and Adam, they apply a HPZ attack, HZP attack, and it requires columns of C from E is equal to CZ, which is just H minus AX, where Z is distributed uniformly. They were able to use 500,000 signatures to break it, and that was pretty much done in a day. So our countermeasure is, as C is rectangular, we may provide that a significant portion of Z has the distribution of our choice. We're currently looking at multinomial distribution. We have tested the attack on this modification with a proper distribution, and with 5 million signatures, no information of C has been leaked yet. So far, the countermeasures do not affect the parameters and efficiency. If anything, we have slightly sped up version 3. An updated specification will be published soon, and we also would like to thank the attackers for their contributions, which have now led to some improvements. Some closing remarks. Our implementations are not fully optimized yet. I'm new to using C. I only started this year, so we look forward to making more improvements on the timing of the scheme and the general implementation. Shorter signatures when compared to most other schemes. The schemes are transparent and easy to understand and implement, which I hope I've proven a point to in this presentation. Version 3 might perform well on 8-bit platforms, as its arithmetic is model a relatively small number, which is Q being 47. And the main operations in both schemes are easily parallelizable because it's just matrix multiplication mostly. And questions.